Good afternoon, everyone. My name is Antonio, and I'm here with Mario to present the results of our project, Air Quality Bias Correction, corresponding to ECMWF Summer Weather Code 2021. Before going ahead, I would like to thank our mentors for their support and expertise throughout the project. Thank you, Johannes and Mija. Next slide. For those who attended the midterm webinar in July, you will be familiar with the next couple of the slides. However, it is important to mention that air pollution affects worldwide population with an estimate of 7 million premature deaths, according to the World Health Organization. These air quality forecasts are necessary. Not only are they crucial for informing citizens about their exposure levels, but they are also vital for supporting policymakers on their daily tasks. In the next slide, we check that these forecasts, as shown in the figure, are biased systematically. In this case, a negative bias is shown, which makes the model underestimate the real observations. This is an important problem. As a consequence, these forecasts need to be corrected in order to provide these people we mentioned before with data as accurate as possible. Now I will leave the floor to Mario, who will talk about the modelization and validation approaches.
Thank you, Antonio. Now, in this next slide, we will present the general workflow. It has been divided into several phases. First, during the pre-processing stage, we have converted the forecasts and the observations available into a structured dataset with features and labels. Then we loop between the modeling and validation stages until a satisfactory solution for forecasting the error in the predictions has been reached. Now we move to present the final model architecture in the next slide. In this case, we have considered 3 different models to extract the most meaningful features of the past and future counts predictions, as well as the station attributes. Regarding the predictions, an inception time model has been used for both the past and the future predictions in order to exploit the temporal variability, whereas a multilayer perceptron is used for the station attributes. Then, all extracted features are fed into another multilayer perceptron to predict the upcoming errors with early resolution. In the next slide, we will explain that we have considered 5 different initializations. Please go to the next slide. Yeah, here we explain that we have considered 5 different initializations of the models considered. Each of these produces a different model that outperforms the CANS model, and all 5 models are assembled with equal weights to have a stable final regression, which reduces the error metrics by around 35%. A model with better performance corresponding to including the latest observations as inputs was discarded during the project development. This was made to facilitate its future integration with the CANS model. This model achieved a reduction of almost 55% of the error metrics. Now we move to the next slide, where we present how the data was managed during the validation phase. First, the dataset was split in 2 different periods of time, one for training and one for testing. For both of these periods, we compare the air quality predictions corrected with the raw CAMS predictions, the observations, and the persistence, which refers to forecasting each day the observer's value of the previous day. This constitutes the validation dataset. In the next slide, we present a slice of the validation dataset for the ozone at the station located at Glasgow. Here, the error metrics for each approach can be easily computed in order to assess the in order to assess the performance of our model. In the next slide, we include some validation plots for the same location, the Glasgow station. In the left plot, the hourly distribution of each variable is represented by a box plot. Here, the blue and green boxes represent the original and corrected CAMS predictions, whereas the yellow ones correspond to the observations. It is clear that our model improves the CAMS forecast significantly, but it does not reach the persistence. In the right plot, the cumulative distribution function of the hourly errors is presented. Here, it is clear that the overall bias is reduced because the CDF is shifted to the left, to where the zero is located. These plots are generated for all air quality variables and locations for both periods considered, the train periods and the test period. And now we move to the next slide, where in addition to the validation plots, we have also considered different error metrics. For example, during the validation phase, we have considered error metrics with respect to different time periods. Some of these error metrics were the residuals, the root mean square error, the mean square error, the mean absolute error, and the error square coefficients. And now Antonio will explain in detail the result of the final model previously presented during the validation process for these error metrics.
So as Mario mentioned, if we can go to the next slide, as Mario mentioned, a set of metrics has been implemented to validate the results on both train and test data sets. In this slide, I'm showing you some of the results. This is the number of stations which present an improvement in both train and test sets in terms of the metric used. So we are showing a table where you can get information about the total number of stations for each variable. You can see that there are 61 valid stations for the NO2, 67 valid stations for the O3, and 102 valid stations for the PM2.5. As shown, there is a bias correction, a successful bias correction of almost 80% of the stations in the worst case, which corresponds with the PM2.5. And there are more than 90% of the stations corrected in the best case, which corresponds to the O3 variable. There's also an increase in the Pearson correlation, which we mean here to the skill of the forecast. In the worst case, 55% of the stations increase the correlation. Which means that there is another 45% which decreases it. In the best case, which corresponds to the O3, almost 75% of the stations increase their skill. You can see more specific information about each station metric in the link provided in the presentation. Next slide. We have also checked the overall improvement for each metric in both train and test sets, which correspond, these values offered here correspond to the average of both train and test sets. You can see here that that overall the bias is reduced for every variable, and that the skill of the forecast is increased as well for every variable. There's an increase on skill For the O3 variable of around 400%, this is due to the fact that it is strongly correlated with the hour of the day and the radiation, which are variables that are provided to the model as features. Next slide. Not all stations have an improvement, as shown in the results table 2 slides before. So we are showing here just an example of an station which doesn't improve the CAMS forecast, the raw CAMS forecast. This is the example of Vienna for the O3 case, in which we can check that the CDF shows the error is just centered at 0, so there's not much to improve. Next slide. Apart from that, we have developed an operational implementation workflow in which we start downloading the data from the atmosphere data store and process it in order to have the proper features prepared to fit our model. We load our model and afterwards prepare the predictions. So we have developed a near real-time operational workflow in which for an station and a variable, we can get the predictions in a fast and easy way. Next slide. With this operational workflow, we have run the simulation for the August 2021 month at Glasgow. We can check that the bias has been corrected and the skill of the model has been increased as well. So this is an example in which I mentioned like a successful case, but there are also unsuccessful cases. If we go to the next slide, we can check that for Montreal there's also a bias correction for the CAMS model comparing to the observations. However, the skill in this case is not increased. In this case, the skill of the CAMS of the raw CAMS is better than our prediction. If we go to the next slide. Here, for the case of Budapest, for the NO2 variable, we can check the same situation. There's a bias correction of the raw CAMS forecast, but the skill is not improved in this case. Going to the next slide, we can check a case in which we don't correct the bias, but we increase the correlation. As we mentioned, the O3 variable is strongly correlated to the radiation and to the local time hour. This is why we get the diurnal cycle very well in this image. The correlation for this data goes from 0.79 to 0.86, even though the bias is not corrected. And I leave the floor to Mario in order to explain you the conclusions.
Yeah, here now we move to the last slide. We try to summarize here the key points of the project development. First, one of the main features of the solution proposed is that a unique model is considered for all stations. One advantage of this approach is that it can be easily extended to new locations even without air quality stations. Another key point is that independent models are considered for each air quality variable. Additionally, the period considered for training includes the COVID-19 lockdowns, which increase the stability of the model as it has been trained with heterogeneous scenarios. Another insight extracted while working during this project is that including the local time at each location allows the model to capture the diurnal cycle of the air quality variables, which clearly improves the model performance. Lastly, the model seems to provide robust predictions even for different CAMS model versions, Here, the model has been trained with a different model version than the one used for the evaluation phase. And to conclude, thanks again to our mentors, and remember that all the code implemented for these solutions, for the processing, the modeling, and the validation part, are available in GitHub. Antonio and I will be very happy to answer any question you may have. Thank you very much.
Thank you very much, Antonio and Mario, for your presentation and your exciting results.